So let's have a look at an example to see what this means exactly. Let's take this sequence in the real line 1 over n. So this sequence is precisely the sequence of numbers so had a bit of an issue there with the pen. Hopefully it's fixed now. So this sequence is precisely the sequence 1 over n. So for n equals 1, 2, 3, 4, etc. So the first term will be 1. 1 over 1 is 1. And then we're going to have a half, and then a third, a quarter, etc., etc. And you can see that these numbers are approaching the value 0. Right? So let's make this formal according to our definition. So this number 0 must be the limit here. That's the limit. So xn, let's measure the distance between our limit 0 and xn. The distance between xn and 0 is given by our standard metric, the absolute value between xn and 0, which is just the absolute value of xn, which is just 1 over n. And that clearly is approaching the value 0. So this distance is approaching 0 as as n tends to infinity. So xn is converging to the limit 0. It's a real number, lies in R. 0 is a real number that lies in R. So we can also write this as xn to 0. And we can pronounce this xn converges to 0, xn goes to 0, xn to 0, whatever we like. And we are precisely defining this in terms of this distance measure. Now, alternatively, we can use the other definition, the epsilon definition. So according to the epsilon definition, if we pick an arbitrary positive epsilon, all of these terms xn for some value of for all n greater than or equal to some value are within a distance epsilon of our limit point 0. So this distance is just xn because our limit point is 0, which is 1 over n. And we need that to be less than epsilon for any epsilon. Well, it doesn't matter what epsilon we choose. For n greater than 1 over epsilon, this condition will hold. Whatever the value of epsilon, we just divide that value. We just divide 1 by that value. And for all n greater than this 1 over epsilon, all of the xn's will be within a distance of epsilon from the limit point 0. So based on this, we can now see why the set 0 to 1 is closed. So let's pick a sequence, any sequence. So we're going to pick a sequence, xn, such that all of the values, all of the xn values lie in this set 0 to 1. They can take the value 0 and they can take the value 1 or any number in between these two values. And furthermore, we want this sequence to approach some limit value x. So two conditions. One, that all of the sequence values lie in this set. And two, that the sequence is actually approaching some limit x. And we're going to keep this sequence totally arbitrary, so any sequence. And we're going to show that this limit value lies in 0 to 1. How are we going to show that? We're going to show that by contradiction. We're going to assume first that it doesn't lie in this interval. the set that we want to show is closed. Now, if we show that this is impossible, that it cannot lie outside this, then it must lie inside this, and therefore any sequence that converges such that all of the values of that sequence lie in this set converges to a value inside this interval, and therefore that interval must be closed. So let's start with this assumption. We're going to show that it's impossible. Now, if this is the case, if x, our limit, is not in this interval, then either it's less than 0 or it's greater than 1. In either case, we can find an epsilon such that this is true. So what do I mean by this? Well, in words, this is telling us that there are no points in our interval, right, that are within a distance epsilon of x. Now, why is that the case? Well, let's think about this. So this is our point 0 here, and this is our point 1 here. So we are considering this interval 0 to 1. Now let's say that x is less than 0. So that means, let's say, x lies here. Our limit point lies here. It's outside this interval, 0 to 1. The set that we want to show is closed. Then clearly we can find some value epsilon. So that's this distance here. And then we can have an equal distance here of epsilon, such that this interval here, which is x minus epsilon to x plus epsilon, has no points in common with the interval 0 to 1. In other words, the intersection of this interval and this interval is empty. They contain no common values. Right? And clearly this is the case. If x is less than 0, then we can always find some value. So the simplest way would be to say, okay, this is the value 0, right? And our point x is, let's say, here, right? It's less than 0. So this x is less than 0. So there's a positive distance from 0 to x. Well, we just pick the midpoint value there, right? We can pick any value between here and here. And for the sake of argument, let's just pick the point here that lies halfway between 0 and x. And so we can define that distance as epsilon. And then we can define another point here, which is an equidistant as this point from x here. And that's our interval. So we can always find an epsilon such that this is true. Okay. So, however, convergence, our definition of convergence, tells us that for any epsilon, there is a number n, a natural number, an integer, such that for all n greater than or equal to this number, the xn are within a distance epsilon of our limit point, x. Now, we are free to choose, so this is true for any epsilon. So let's choose this particular value of epsilon, because we know that if this is the case, either x is less than 0 or x is greater than 1, then we know that there is definitely an epsilon for which this is the case. So let's choose this particular value epsilon in our definition of convergence. So then this must also be true, that almost all points are within a distance epsilon of x, our limit point, which lies outside 0, 1. So, as I said, almost all of these points are within a distance epsilon of x. but this means that they lie outside the interval 0 to 1, which is a complete contradiction because we defined the sequence as having all of its values inside this set, right? So we've reached a contradiction, and that tells us that if we have a sequence whose values, the values of all of the elements of this sequence lie in the set, then its limit must lie in the interval 0 to 1. And so this interval, this set, is closed. So based on this, we can now also see why this set cannot be closed. So let's take this sequence. Xn is 1 over n plus 1. Now notice that all of these values will lie between 0 and 1. Right? And as n tends to infinity, these values will approach 0. So let me make this absolutely clear. So what is this sequence? Well, the first value will be 1 over n plus 1, so it's 1 plus 1, so it'll be a half. Then we'll have a third and a quarter, etc., etc. And all of these lie between 0 and 1. Now, they are approaching 0 as n tends to infinity, right? As n tends to infinity, these values are approaching 0. So for any epsilon greater than 0, let's see what the distance is of xn from 0. So xn minus 0, the absolute value, will just be 1 over n plus 1. And we need this to be less than epsilon, which it will be for all n greater than 1 over epsilon minus 1. So indeed, xn is approaching 0. But here's the key thing. The value that it's approaching, the limit, doesn't lie in this interval. So this limit point of this sequence, the limit point 0 of this sequence, doesn't lie in our set 0 to 1, which excludes the point 0 and the point 1. But crucially here, we're excluding the point 0. Right? And therefore, 0 to 1 cannot be closed because it doesn't include all of its limit points. Now, we could equally as well choose the value 1 and find a sequence with all values inside our interval, but which approach the value 1. So actually, let's do that. Let's, for the sake of completeness, let's actually do that. So let's think of a sequence whose elements are entirely inside this set. So we could think of 1 minus 1 over, I guess, n plus 1. Let's check this. So this is a sequence for all n belonging to the set of natural numbers. So this would give us, so for n equals 1, we're going to get a half, 1 over 1 minus 1 over n plus 2. And then we're going to get 1 minus a third, which is 2/3. And then 3, we're going to get 3/4. And then what we're going to get n, so that's n equals 3, then n equals 4. We're going to get 1 minus 1 over 5, so we're going to get 4/5. Of course, I'm being silly here. So the general case, of course, this is just it's going to be the general case will be n minus 1 over n, right? That's what we're going to get. So this is approaching the value 1, right? So the limit point is 1. but all of the terms lie between 0 and 1, right? So we have a sequence which has all terms lying inside our set, and which is approaching some limit, but that limit does not lie inside our set. So it doesn't contain its limit point. And we only need to find one sequence for this to be true to know that our set is not closed. And we found two. We found one that is approaching 0, and we found another sequence that approaches 1. Okay, so um, so that now we have quite precise definitions of what we mean by an open set and what we mean by a closed set, right? And we also now know what sequences are. We have a notion of convergence, one definition of it in terms of sequences. So we've learned quite a lot there.